Oh, we already have one guest. Yes. It is lecture number 23 in the computational chemistry course. We do have, as usual, the biggest possible challenge is to match time schedule. You all accumulated so much knowledge and information, and you are so eager to share it that it is very difficult to fit into 3, 4, maximum 5 minutes presentation. So please watch time. If you will go longer than assigned, I will just come up and stop. So try to speed up. The idea is that we do have 1 minute to come, 1 minute to leave, 3 minutes presentation, 3 minutes questions. But it can be modified a little bit for the 4 minutes presentation, 2 minutes questions. For the visitors, who are very welcome, for the visitors, you are very welcome to ask questions and support scientific discussion, but please make note that we are on a tough schedule. Each talk is like 3-4 minutes and questions no more than 2 minutes. If you fail the schedule, we will be kicked out and the last speakers will have no chance to present. So we are living a tough life. This is a computational chemistry course. The goal is to provide students in engineering, math, chemistry, physics with practical skills to model, to characterize materials. The course is composed of 3 main components: theoretical background, practical skills, and scientific communication. As you see, today we will practice scientific communications, presenting our practical skills. Before we learned different pieces of software, but now we are focusing on a specific piece of software named Vienna Ab initio simulation package, which is designed to model not only chemical systems, but chemical systems interfacing solid surfaces, liquids, gases. And upon completion of this set of presentations and accumulating these skills, we are going to try to apply those to modeling realistic materials and predict several observables, such as chemical stability, magnetization, band gap energy, absorption, photoluminescence, spectra, and reaction barrier for bond breaking and formation. So with this session, with this piece of software, we are trying to go further than we did with other pieces of software, because we are having at least 3 new challenges that will be addressed by each of presenters from different angles. So first, periodicity. If we depart from isolated chemical molecule to periodic models, there are specifics for periodicity. Second, spin multiplicity. If you depart from singlet closed shell molecules, one needs to make special arrangements for spin. And third, if there are chemical reactions that we are interested in, we need to have tools to track bond breaking and formation. With this, I would like to bring your attention to the schedule, which consists of 10 talks. We will try to follow the schedule, and today meeting completes 4th chapter in the course. There will be third chapter. There will be a 4th chapter also finished with presentations, and I would like to bring your attention to the fact that your presentations are placed here. They are numbered according to the order, 1st, 2nd, 3rd, and they have name of the presenter in the name. So 1st, 2nd, 3rd, so you will be able to navigate. So I'm opening the first one, bringing it, and you will be seeing the title page, but then you will see your own title page. Okay? So with this, I would like to invite H.M. Faisal Nasrallah to give an opening talk on the input that one needs to communicate to the WASP software to make it run. Floor is yours. Please be short. So here's keyboard, mouse, screen, point on there.
Hi everyone, good afternoon. This is HM Nasrullah Faisal. Today I am going to talk about the goals and responsibilities of DFT and preparation of input files for V8 for WASP. Actually, density functional theory, abbreviated as DFT, uses the electron density to find the energy of a molecule instead of wave function. Actually, it is one of the newest definition methods and it has become popular due to less intensive calculation. It was originated from the theorem by Hornberg and Kohn, but the original theorem was used for the ground state electronic energy of a molecule. The practical application of DFT was developed by the Kohn and Schramm. In DFT, the electron density is actually expressed as a linear combination of basis function known as Kohn-Schramm orbitals. A determinant is formed from these orbitals which is used to compute the electron density. The Kohn-Schramm orbitals are not mathematically equivalent to Hartree-Fock ones. A whole list of density functionals are used as the exact density functional is unknown, and these functionals are developed either from quantum mechanics or by parameterizing function. In density functional theory, the integrals for Coulomb function is needed to be done over the electron density, which is scaled as n cube. In case of Hartree-Fock, this is scaled as n4. That's why the density functional calculation is quicker than the Hartree-Fock calculation. Density functions can be broken into several classes, and the simplest one is the local density approximation. For high spin systems, it is known as the local spin density approximation, and it is widely used for the band structures. The accuracy of the DFT can be poor to fairly good depending upon your choice of density functional and your choice of basis sets. For organic molecules, the B3LYP hybrid potential with 631G basis set is most popular because of its effectiveness, but the accuracy and effectiveness of DFT is not very good for the heavy elements, the charge system, and the systems that are sensitive to electron correlation. Now the WASP. The Vienna ab initio simulation package is a computer program computer program for atomic scale materials modeling like electronic structure calculation. It computes an approximate solution by using DFT or Hartree-Fock or by combination of both. In WASP, the one electron orbital, the charge density, and the local potential are expressed in plane wave basis sets. The interaction between the electrons and ions are represented either by pseudo potential or by the projector augmented wave method. Now the most important input files for WASP are POSCAR, POTCAR, INCAR, and K-points file. The POSCAR file, it contains the lattice geometry and ionic positions. Sometimes it also contains the starting velocities for an M-Durand. The POTCAR file, it contains the pseudo potential for each atomic species that comprise the molecule. For the K-points file, this contains the coordinates and weights or the mesh size for creating the K-point tree. And the INCAR file, actually it is the central input file for the WASP. It determines what to do and how to do it. So that's our structure. There's the cyclohexane structure. We made it in Gaussian and then optimized by Hartree-Fock. Now if we need to make the POSCAR file, POSCAR input file, we need to convert this Gaussian structure into XYZ file, and that's why we convert this Gaussian Hartree-Fock file into the XYZ file, and then we convert this XYZ file into POSCAR file. If we need to edit this POSCAR file, we type the nano POSCAR and then we will get this file, and we will remove the unexpected lines from it and we will make a clear one like that. Now we need to rotate the XYZ as we need to align it according to a required orientation with respect to XYZ axis, and then we need to put the angle of rotation around X, Y, and Z. As a result, an intermediate POSCAR.tint XYZ will be created. Now we need to define the periodic lattice vectors, and we need to put the lattice correction on the X, Y, and Z axis, and then we submitted our POSCAR file. Then we need to make the in-car file, that's the in-car geometry optimization, and if we type the nano in-car, we will get those different modules that control this operation. In this case, as it is a single point charge calculation, we change the NSW from 150 to 0 like that, and then save it. Now the K points file, for the K points file, we will write this code CP bin K points, and it's done. And the last one is the podcast file. It is the potentials of each atom, and we need to write this code, and in this case these are the atoms that comprise the molecule, and they will be ordered according to the alphabetical order. Now we do have now all the files. If we put it in, we can look the podcast, K points, in-car and post-car, and now we can run our VSP, and that's it.
Okay, thank Faisal. So, any questions to whatever he presented? Please.
So, do you use serial version or parallel version of WASP? So, if you use parallel version, how many processors is the optimal number in the calculation?
The larger the better. Just tell me.
How many processors you usually use? 8, 16, 100? Oh.
Just tell me. I'm not on the camera.
It's actually 4. Actually, 4.
4? Only 4? And I use
Small system.
it's a very small system.
More questions?
So you said that heavy elements were not DFT friendly. How heavy? Are we talking uranium, iron, potassium? What? How big? How far down the periodic table is DFT still useful?
I think the heavier ones like
Okay, more questions? You gave practical steps how to prepare input file for positions. If you do not use periodic models, if you use chemical models, what are the good values for this periodicity adjustments? Approximately.
Yeah.
0,
0, 0.
Just what are you showing here? How much vacuum do you add to simulation cell? In which units are those numbers?
There's certain lattice corrections.
Yes, in which units?
Angstroms.
Good, thank you very much. Thank you, Faisal, for a nice presentation answering questions. And with this, let me invite next speaker to the stage, which will be Tion, Nakasinka, and Mindika. So, next speakers, please try to approach and set up your presentation while we are going through a session. And just one more announcement. One of the side goals of this session is that one person becomes expert in one aspect, another in another aspect, and then we communicate, so to say, verbal manual how to operate this software. So it is not just to show how nice I know about it, but it is a little teaching assignment, communicating skills. Okay, with this, Tion Mindika, PhD candidate in the surface chemistry, will present which output WASP software is providing. Floor is yours.
Okay, good afternoon everyone. So during my presentation, I am going to show you how to extract some important information contained in WASP output files, and also how to visualize so-called Cornsham orbitals. So, as Faisal discussed earlier, we can run a WASP job using this set of input files, this postcard, podcast, in-car and K-points file. And if we run a WASP job using this set of input files, a set of output files will be generated like this. So if we generate this set of input files, this will contain unique pieces of important information. So for example, this conca file contain updated geometry data such as lattice points, Bravais matrices, ionic positions, etc. And these waveka files contain the important wave function informations, wave function coefficients. OCK file contain short summary of the results. So we can use this conca, chargeka, and waveka files in continuation jobs such as molecular dynamics calculations. So in my part, I'm going to so using outca file, we can extract some important essential information for a particular system, such as total energy, band energies, Formaloom energies, etc. So using an example, output file for titanium hydroxide, which was optimized, which was with a single point optimization. I'm going to explain how to extract total energy and band energies for this particular system. So if you want to extract total energy of this system, if you have the outca file, we can use this command line with the command grep and this keyword free energy. We can extract the total energy with this command line. So it will give the total energy in electron volts. So if you want to extract number of bands of this system, which will be a important input in lot of calculations or a lot of calculations, we can find out the number of bands in the system using this command line grep and the n bands keyword with this outca file. We can generate the number of bands in the system, and if we can generate the band energies, we can find the band energies of this particular system using this command line grep, and this is the number of bands in this particular system and the keyword band energies and our outca file. So this will be the output. So if we know the band energies, we can find out the highest occupied molecular orbital and the lowest unoccupied molecular orbital. So here you can see the band number, band energies and the occupation. So if we know the energy of the highest occupied and lowest unoccupied molecular orbital, we can find out the band gap in electron volts. So these are some essential information which we need to know about a molecule. So now I am going to explain briefly about how to visualize Kohn-Sham orbitals using this WASP output data. So Kohn-Sham orbitals is an analog of molecular orbitals in Gaussian. So in density functional theory, Kohn-Sham orbitals are defined as some set of auxiliary quantities which can be used to calculate total charge densities and the total energy. So this relationship shows how to use. So here we can see the relationship between the total density and the Kohn-Sham orbitals. So if we know the Kohn-Sham orbitals, we can determine the density, and if we know the total density, we can determine the total energy, because total energy is, we can represent the total energy as a functional of the density. So to visualize Kohn-Sham orbitals, first we have to generate these Kohn-Sham orbitals. So to generate these Kohn-Sham orbitals, we can use we have to use set of input files. We can use the output files of the optimization job. So here the positions, we can use the positions of this output conca file as the posca file of this input as the input file, and then we can use the same k point and the potentials for this calculation, and also we can use the waveka file from this output file of the optimization job, and we have to import we can import the necessary Inca template which is necessary to run this particular calculation job. So we have to import this. We can import this Inca template, and we can modify this template according to our system. So in this case, I am doing optimization of the titanium hydroxide molecule. So which has so this is the Inca template. I have to modify this according to the according to this molecule. Here I have 24 bands in this molecule, so I have to modify this, and I have to modify this part energy interval, which is characteristic to the band energies of this molecule. So after modifying this in car file we have all the necessary input files so that we can run this calculation. So it will generate this output data. So here you can see these partial charge densities, which are the Kohn-Sham orbitals for each and every orbital in this molecule. So if we since we have these partial charge densities for the Kohn-Sham orbitals, we can visualize these orbitals using any kind of software like Gauss view or WASP view. So here I am going to show you how to visualize this using WASP view. So I'm going to visualize the molecular orbital, highest occupied molecular orbital of this titanium hydroxide molecule using WASP view. So this is the WASP view data viewer window. So we can open this molecular orbital, highest occupied molecular orbital of this titanium hydroxide using this WASP view software, and then we can customize this window using these tabs, data, atoms, bounds, view and options tab, to obtain a nice image of this molecular orbital. So that's all I have. Thank you.
Okay, let's thank Tilan and Kasinka for a nice presentation, and floor is open for paper is open for discussion. Any questions to Tilan?
So a quick comment. Instead of using WASP view, you can use Vesta. Vesta is also quite good to
Vesta?
V-E-S-T-A.
Okay.
It's free software, very similar to Crystal Vector or something, and it's free. And it's for visualization. It looks really good.
Can you directly visualize using the WASP view?
Yeah, you can visualize charge densities and
if you want to do like,
in general,
if you want to use Gauss view, we have to generate the cube files, so we can directly do. But
yeah, for Vesta you can open the Chakra file or Parka file directly. You don't have to do any conversion, because in the past I remember I had to do conversion, but with Vesta it's quite convenient.
Good. Thank you for the comment. More questions to the speaker? Which orbitals do we see here? S, P, or D? On which atom are they localized?
P orbitals.
Yes, very good. Let's thank Tilan once again. So the next presentation is by Aaron Fordy, and he will help us to address one of the He will help us to address one of the key challenges for periodic systems: the ability of all system of electrons to travel with a specific momentum. Floor is yours. We are about 5 minutes behind the schedule, but so just try to be quick.
So I'll be explaining the purpose of the K-points file that we use in WASP. So before going into WASP, we're going to explain what a K-point is physically. So comparing small molecules and periodic structures, if we have an acetylene molecule, we can model it as a particle in a box. So if it tries to move, the electron will just kind of bounce back and forth, and here it'll produce a standing wave and have a zero average or zero group velocity. But if you're in a periodic potential well, like a polyacetylene molecule, the electron can tunnel through with these potential barriers here, so it can have a velocity in one direction. So if the electron has velocity, it can have some momentum. And then using the de Broglie relation, we know that momentum is h over lambda. Making use of a convenient change of variables to make it a linear equation, we can change it into the momentum is h bar k, where k is 2 pi over lambda, or the wavelength of the electron. So that is the k that is referring to for k points. So we're essentially plotting electron momentum with our k points file. So as you can see in the fourth row, the 1, 1, 1, that corresponds to plotting one k point in the 3 k point directions, x, y, and z, for your periodic directions. So if you change those, like we change the first column into 4, that'll plot 4 k points along the x direction and 1 along the y and z. So you just have to know which direction your model is periodic in to change the number of k points that are sampled in that direction. And so if the electron has changing momentum, it will have changing energy as well for each orbital, which will lead to electron or energy dispersion in the periodic crystal. And thankfully, it's periodic throughout the crystal as well, the dispersion relation. So we just have to sample the smallest repeating unit, which is the Brion zone. And that's where the K point sample. And then the Brion zone corresponds to the lattice vector for the length. And then the wave function solution is the general solution of the Bloch function, and that's what is plotted into to get the energy. So if we have our wave function, we can get our energies. And on the right, that shows just the dispersion relationship for transpolylene and acetylene. So how do we practically generate the energy dispersion files? So for here, I just plotted the HOMO and the LUMO. And we say we run VASP with the desired amount of K points. And we inspect our outcar. We'll have a bunch of K points by clusters. So for K point 1, we'll have a K value and a bunch of energies. Like different K point will have different energies for the same orbitals. So here I'm plotting the HOMO-LUMO, so 10, 11 orbitals from the output. So first we want to extract the K points. So the top line just explains how to pull out the K point files and save them as a KK file, which shows the 4 K points that I plotted. And then we want to extract the orbital energies, so grab the 10th orbital energy, save it as K10, and it saves the 4 corresponding orbital energies for those K points. And then do the same thing for the 11th to get the LUMO orbital energies. And then we want to merge all those into one file so we can plot them using NuPlot. And then we have to have them in columns because that's how NuPlot reads it. So using this top file, that merges them all into an energy dispersion file where we have our K points, HOMO, and LUMO energies. And then we can just write up a little script for NuPlot to plot each of those. And then get the nice little graph that I have on the right showing the energy dispersions for the HOMO and the LUMO. So in summary, for molecules, you only have to plot 1 K point since it doesn't have any change in momentum. Periodic structures, you have to plot multiple K points along your periodic directions. And then K points give instructions how to plot the K points so we can plot our band structures for the materials.
We thank Aaron for the presentation, and questions are very welcome to be thrown at him.
The student have to ask questions.
Yes, and I'm recording. Well, it is on record who is asking and who is not asking questions.
Okay. So, how do you choose which direction that you vary the K point value?
You mean in the VASP?
No, I mean you have to choose different K point along a certain direction, right?
Mm-hmm.
How you choose that direction? How do you know which direction you should get?
So if we look here, like this will correspond to the x-axis.
Okay.
This column, the second column is the y, and the second column, or the third column is the z.
Yeah, but which direction that you should go? Like, it depends on the molecule that you're looking at, right? It depends.
Oh, you just have to know from when you make it, I guess.
So, for example, you can choose from the gamma point to the X point, or the gamma point to the Z point,
Oh,
or the
you
gamma
mean
point to the L point in the Friedmann zone, right? So, which direction that you have to choose?
Oh, so that would be the bottom row. So 0, 0, 0, that's the gamma
Yeah.
symmetric, and then I'm not too familiar with reciprocal space, how to switch them around, but you do that with the last row.
Let me reformulate the question by Dr. Kang. Are you dealing with 2- and 3-dimensional periodicity, or you are focusing on 1-dimensional periodic systems only?
For this one, it was
That's easy.
one.
Okay. Yeah.
More questions? I do have one.
Okay.
So, can you go to your computed dispersion? Yes. So, the systems where minimal energy between HOMO and LUMO appears at the 0 momentum are named direct gap semiconductors. The systems where the minimal energy at non-zero momentum are called indirect gap semiconductors. Do you have here illustration of direct or indirect gap?
From there, it looks like a direct gap.
Yeah, but very good. Let's thank Aaron. And with this, the next presentation will be by Whitney Ong, and she will continue the aspects of characterizing materials with the WASP software, and she will address the practical way to estimate the gaps, to illustrate what are the gaps, how to compute, and how to process output of WASP. Floor is yours. We are almost in time, thanks to Aaron.
Okay, so I'm Whitney, and today I will show you how to plot density of states and molecular orbitals using WASP. So brief introduction, density of states represents the number of states per interval energy that can be occupied at each energy level. So if you have a high density of states, means you have many states available for occupation, and if you have a zero density of states, means you don't have any states that can be occupied by electrons. So the molecule I use to optimize all my structures is C4H4, because this is the smallest molecule that I can run with single K point. So after optimizing your structure, you should run a single step job by modifying your in-car file. So first of all, you make a new directory to put everything in there, and then you copy, this is the most important one, you copy your current car file and you name it to postcard in your in-car, to your new file, and then you copy your K points, pod car and in-car file, and then you make changes to your in-car file. So first of all, you have to make sure your to make it into a single step job, change the NSW equals to 0, and then if you have different electronic configuration like cationic or anionic state, you have to state the number of electrons in your system, and if your system is in excited states, you have to change your isomer to -2 and add the line fairway for number of occupied molecular orbitals multiplied by 1, and then you type 0, 1, and then number of unoccupied molecular orbitals by 0. So here's the example of the in-car file. Your NSW should be 0, and this is added according to your electronic configuration. So after the job is done, the density of states can be plotted, but a few informations are needed. So you need a number of states, you need a number of electrons, number of atoms, and the Fermi energy and alpha and beta energy. So first of all, you also have to generate a states file. You can get the band energies from the states out card and put it into a states file. And in the states file, it's important to delete the first row because we only want the values and not the wordings. Otherwise, it wouldn't work. So, and then it's important to look at the number of band, a number of orbitals, and then you look at which interval you want. So, for example, I want a -9 to 1 electron volt, just a few above the HOMO and few below the LUMO to plot your graph. And then you can get the number of electrons for your outcar file. You can also obtain your Fermi and alpha and beta energy from your outcar file. And then you run the script to generate the density of states, and then you answer the questions according to what you want. And then you can set up your parameters of the graph as well. So this will, you can find your energy and Fermi and alpha and beta. And then if your job is succeeded, you should get this tree line of I am still okay. If it's not okay, well, usually you have one line and then you have error down there. Then whatever new files that is generated will not have any information to make your file. So make sure you have these 3 lines, and then you can move on to the next step. Usually the error comes from you forget when I forgot to delete the first row from the states file. So then you can plot your graph and convert to PDF, and then copy to a local computer and view your file. So the results can be very different from ground states, anion, cation, and excited state. The red color shows that the orbitals being occupied by the electrons. So you can see that in anionic state we have extra electrons, so there's more electrons occupying the orbitals, and then in cationic state we have less electrons occupying it. In the excited states we can see the flipping, or the excited states of the electron occupying the next state instead of the state. So if you want to visualize your molecular orbitals instead of from the graph, so you also have to have your optimized structure, and then you should make a new directory because it will have quite a lot of orbital files being generated. So make a new file, and then copies the following files, K points, plot car, and one more extra file that you have to copy is the wave car. And then Again, copy the con card instead of postcard because we want it from the final data, not the initial data. Otherwise, you will not get anything at all. And then in-car file can be copied from the template in the cluster. And then you also have to modify some changes in your in-car file. So things to consider is your number of orbitals in the n bands and the range of orbitals you want. So earlier I wanted a few above the HOMO, a few below the LUMO. And yeah, and then I just put like -9 to 1 electron volt. And then same thing to go with your number of electrons and your Fermi wave if it's in the cationic, anionic, or excited state. So this is a typical in-car file. So your number of bands and then your ENIT should remember to change that, and then your last line always can add all the changes. And then you will see many new files can be generated. You can just make both one HOMO and LUMO, but usually you want a few, then you can visualize it in the WASP. You can copy all these files to the local computer and view it using the WASP file. So go through briefly using how to use the WASP view. So in your data tab, you can adjust your isosurface and see if you want to draw the slice. In the atoms tab, you can adjust the atoms radius. In the bound tab, you can extend or shrink the bounds. In the view tab, you can zoom, rotate, or move the molecules around, and miscellaneous options can be found in options tab, like changing the atoms color, background, things like that. So this is the results of seeing. You can view different orbitals from the HOMO and LUMO state. Yeah, you can view it in the WASP view. So in conclusion, 4 basic files is needed to run the Java postcard, podcast, K-points in DOS plots. You need to run a single job stat, and you also have to adjust it based on your electronic configuration. And in molecular orbitals visualization, the most important thing is you need an